yesterday, we'll be passing the presence list. So please sign it up. It will be available for the next 5 minutes. So if you have someone that arrives here while you are signing, please let he or she know. But I will collect the presence list when Fabio is done with his solution of exercise. And as you know, everything is probability distributions, right? So if you have a time t to arrive, right? And if you plan that in the mean you will arrive at time t, you know, in the mean you will arrive at time t, but that means that half of the time, if the curve is symmetric, you'll be late. So, you know, I'm talking this to you, you are the guys that were ahead of time, but, you know, tell your friends that you have to think this, right? Plan that you will arrive in the mean before time, so that, you know, perhaps we get a 2 sigma here, and, you know, 98% of the time you get in time. So that's just tell your friends that you always have to plan to arrive earlier, so that as a probability distribution, you get in time more often, right? But I mean, the point is that it's probabilistic. So, you know, you always have to plan ahead because of there is a probability distribution. That's the key thing of arriving in time. Okay, so yeah, thanks. Let's go.
The one created by dark matter. Of course, you can complicate the problem, but for a start, that's the case. So the first thing that I asked is, okay, I know that this is the rotation curve, and that's that depends on the enclosed mass of dark matter, because I'm saying it depends on the dark matter. And the question is, if I have only one observation, only one of the rotation curve, which is what I can observe, can I tell the density of dark matter at that point? Okay, that's the question. It's very simple. And this has nothing to do with astrophysics. It has to do with integrating functions, right? So the enclosed mass is what? The enclosed mass at the given radius is going to be the integral from 0 r of r square, well, I call this r prime square rho dm of r prime, the air, because I'm assuming that it is spherical, and then there is a factor pi somewhere that in this moment I really don't care about. There is also a constant, then the constant that in this moment doesn't really affect our studies. So this is the thing, so I can just plug this in here, right? So I know that r d square is equal to the integral of r prime square rho dm dr from 0 to the radius of my interest. Correct? Now I want to express everything in terms of rho dark matter, because that's what I'm interested in. So I have the derivative of the first term is nothing else than b dark matter square, the radius r, plus the radius multiplied d squared there. Correct? That's the first term. I've just made a derivative. Must be equal to r square right? Constants aside. Am I doing anything wrong or strange? And at this point, I just solved this. So I know is equal to what? To okay, now if you rearrange these, you can actually see it in a more elegant form, and you have the logarithm of the velocity over r. But the whole point, And of course, when I make the observation, I know what my radius is. But the whole point is that if I want to know the dark matter density at any given radius, I have to know the velocity, but I also have to know the derivative of the velocity in that point. So I cannot tell the dark matter density in one point with only one observation. I need to know, I have to have the observations that in other ways they give me the derivative. Okay? First part of the problem. Second part of the problem that I was asking is, I still am in a region which is dominated by dark matter, and now I have observation at different radii. So I know that the dark matter, that the velocity is constant, okay, in that region. What is the density profile that I need? How must dark matter be distributed, assuming that it's spherically distributed? That's the only assumption I'm making, and it's fully sustaining the curve, in order to make that curve. Okay. Now the thing is always the same. I have that I basically have this. Actually, I prefer to write it in a different way because it's more convenient. So v square of dark matter as a function of the radius is equal to g over r integral of r square dark matter dr. Right? Well, this should be primes, but doesn't really matter. Okay? And now I'm telling you, this one in this specific part of the problem is a constant, right? So I can easily write this over G Is that correct? I just moved stuff over here and I said that v square is a constant, k. Now I play the same game. I just do the derivative with respect to r on both sides, and what I get here is so on this side I get this, and on this side what I get k over g, which again is a constant, multiplied by this, plus 0. Right? So I get that rho dark matter multiplied by the square radius is equal to a constant, another constant. So I basically have this is telling me that if I want a flat rotation curve, I need to have something like, if it's entirely supported by dark matter, of course. So this is exactly what simulations that solve the equations of the evolution of a collapse in a potential find in the outer regions. In the innermost part is a little more debated. There is something more complex. But if you take simulations, either dark matter only or even with the formation of galaxies and baryons, in the outer part they basically always find this. And it's amazing because this is analytical, purely analytical. Okay? You can do it with calculus 1, right? I think it's time for Farinaldo to take on the class. Everybody's in. Let me switch this off.
Okay, now we go with Farinaldo Queiroz, who's actually a new hire at the International Institute of Physics and also associates to here, ICTP-SAIFR.
Hello, hello.
Next two classes are by him. And please return the list. Yeah, I'll get there. Thanks.
Okay, so I want... Was there a question for someone? Oh. So I won't waste any minute. First, please raise your hand, everybody who is familiar with the Sena model of particle physics. Okay, not the lambda CDM. The Sena model of particle physics. Okay, the majority. Okay, that's good. All right, and who is familiar with the lambda CDM model? You. Okay. Who is familiar with nuclear physics? Most of them. Who is familiar with neutrino physics? See? Many. All right. So that's the problem. The dark matter problem involves all of them. Okay? So if you try to interpret dark matter in terms of particle physics, you sort of have to have a hand on different layers of physics in different areas of physics. That's why it's complicated. Okay? So I usually advertise dark matter like the propagandas that happen in Brazil. Even in the US, they say dark matter, for instance. Is easy. And then put stars, and here is very, the fine print is you need to understand nuclear physics, particle physics, cosmology, bit of astronomy, and neutrino physics. Okay? So that's the dark matter problem. So today, I'll be talking about dark matter, the production of dark matter in terms of particle physics. I have just one goal in the next 2 days, so it will be very clear in the next slides. So before showing what this goal is, first the things I'm going to cover in the next 2 days, doesn't really matter if I'm going to cover all that. As long as you absorb the material, this is enough. So I'm going to give an introduction of what cold relic and hot relic is, and then go through the production mechanism of dark matter, the most popular ones. So it's very ambitious goal, but let's see how we go. My goal is the following. So my goal is that almost everybody can have an idea of each one of these animals, okay? Of each one of these animals. So for instance, these are the zoo of dark matter candidates. So we, as Fabio mentioned previously, we don't know the nature of dark matter. So we don't know what dark matter is in terms of particle physics. So there are several candidates in the literature, and I just put an animal associated with each one of these candidates. So for instance, the wimp that I'll be talking today and tomorrow is like the Lion King. So it's the most popular and perhaps some of the most compelling, not the, I would say. It can be, I find it the most compelling, but I'm being biased. So it's still the king, but you have something like the axon that if he dies, it will be my turn. It's probably the second most popular dark matter candidate, and you have several of them. So if I have time, I'll be talking about all these candidates, how are they produced in the early universe, and how you can have a concrete particle physics models for each one of these candidates. Okay, let's see if we will go through that. Anyways, so just to keep everybody on the same page, the majority has seen the standard model, is familiar to the standard model of particle physics. So in the standard model, Andre has mentioned that we had some discussions about stellar neutrinos. People ask questions about stellar neutrinos, if stellar neutrinos can be dark matter. And I'm going to prove using Mathematica, easy Mathematica, that neutrinos in the standard model cannot be dark matter. So I'm going to prove that to you. And it's actually one of the exercises I'm going to show. So you have a step-by-step exercise where you're going to prove that neutrinos in the standard model cannot be the dark matter. Okay? It's simple. And if stellar neutrinos can, and tomorrow then I'll have an exercise where you're going to prove that stellar neutrinos can be dark matter. But in order to get that, we have to see the lecture on tomorrow. Okay, so this standard model particle physics, you have these symmetries, which gives a unified description of strong and electroweak interactions. And in the standard model, we have these quarks and leptons, and these gauge bosons here on the right, and including the Higgs boson discovered in 2012. And none of these particles can be the dark matter. I'm going to prove this soon enough. This is very important to capture because if the standard model particle, which are the parts we know today, cannot be the dark matter of our universe, it means that we have to go beyond the standard model. Okay? Beyond the standard model. That's why it's so important and compelling. It's one of the reasons, it's not the only one. That's the reason why beyond the standard model physics is so important. So I'm not going to go through this. So Fabio has nicely presented the sum of the evidence for dark matter. So he has given you a grasp of the evidence of dark matter. Okay, it's not, he hasn't gone even through half of them. So I won't go through that. The only thing I needed to remember from his talk today is that this critical density, so since just few of you is familiar with lambda CDM, so the Friedman equation is k over a squared and the whole over 3. So the Friedman equation, which governs how the universe expands, if we've seen, so Fabio has mentioned, but we know that the universe is flat. K is the curvature of the universe. This is 0. Throughout my talk, I'll be talking about the early universe where the cosmological constant is not dominant, so I'll neglect that part. So I'll just be talking about this factor here, where H is A dot over A, where A is the scale factor, which relates the physical densities to the comoving density, distance. Anyways, and this critical density is just 3, I just go back here, 3h squared over 8 pi g. So rho c is the critical density, is the density of a flat universe. And rho h, if I take it today, the Hubble rate today, which is about 100 h kilometer per second per megaparsec. So you just replace that, you get what rho critical density is. So you're gonna need that number for the exercise. Okay, so that's all you need to know. And the dark matter density at cosmological scales, or the abundance of dark matter, is around 0.3. So the exact numbers are irrelevant throughout this talk. You just need to have an idea of the order of magnitude. All right. So you've seen, Fabio has mentioned that we use this thermal production, thermal freeze out of species in the early universe to understand how much baryons we have. That's what we call the BBN, Big Bang nucleosynthesis. We've seen that photons at some point belong to a thermal freeze out, and you can, from that is very easy. You can compute the decoupling temperature of the CMB. So use this thermal guiding principle to determine the decoupling temperature of the CMB. One thing that you might think is that since we've used this thermal equilibrium principle to explain Big Bang nucleosynthesis and to explain CMB, it's a very good guess that maybe dark matter particles belong to also a thermal history. It's a guess, not a proof. But it might be, right? It's plausible. We explained in the past observables in nature using this thermal equilibrium guiding principle. So why not dark matter particles also belong to this thermal history? It could be. So it so happens that if this statement is true, so remember, I'm not talking about which model in particle physics, which candidate, none of these zoo of candidates. I'm just saying, if the dark matter particles belong to a thermal history in the universe, the cross-section, the interaction rate that these dark matter particles possess, are at the weak scale. What I'm trying to say is are similar to the ones that we know in the Sona model. So the dark matter particle interacts something like the things we already know. And that's very important for searches for dark matter. So you're searching for something that is like, resembles the Sona model. So this is a very good guess. And this thing, weak scale, so that's why the terms also weakly interacting massive particles, WIMPs. So you could ask if that's a WIMP. Okay, so for the boys in the room who have watched this, ask if you are a WIMP. And that sounds to be, for me, a very good guess. So now let's compute things a little bit. So I'll go slowly. Yeah, it has to be stable anyways. That's one of the demands to be dark matter. It has to be stable at cosmological scales. That's one of the things that Fabio has mentioned Because if decayed, we would have seen already, well, the lifetime of the dark matter particle has to be much, much larger than the age of the universe. It's not just about the age of the universe, it has to be much, much larger, because the probability of one particle decaying, we would have seen it already. So the lifetime of a dark matter particle has to be like 6 orders of magnitude larger than the age of the universe. Yeah, yeah. So if the point is, if belong to a thermal history, that will happen anyways. Because if it belongs to a thermal history, it might have been connected to the standard model particle somehow. They've connected to the standard model particle somehow. Whatever it is decaying into belongs to the standard model spectrum. So I will see them. So whether it's neutrinos or electrons or whatever. But obviously you can have a confined sector of dark matter, but I won't go through that. So the deal is the following. So imagine you're going to see this formula very often. When, in order to compute the decoupling, or to determine the decoupling of a given species, you need to compare the interaction rate of that species to the expansion rate of the universe. So that's all you do. That's this simple comparison, which I call gamma and H. H, you've seen already what it is there on the board. So I'm not going to prove this to you, but you can use dimensional analysis to determine that gamma is equal to this. So it's the following. So imagine the interaction rate of a given particle, whatever that is. That's the formula. Doesn't matter which species. Gamma is the number density of that particle, and sigma v is the cross-section times v is the relative velocity between these two particles, incoming particles. And the expansion rate is the number. You compare these two. So if I define reduced Planck mass as this, 8 pi gn, just that, you can rewrite the expansion rate of the universe in terms of the reduced Planck mass and the temperature. What is this temperature? Would anyone answer what does this temperature mean? Perfect. Why of the photons? Because remember what I said in the very beginning? I'll be talking about the era of the universe which was radiation dominated. So this is, the universe is flat, there is no lambda involved. So I'm talking about not the matter radiation, I'm talking about the radiation dominated era. And when the universe was dominated by radiation, the things that were radiation at that time were neutrinos and photons. So this, roughly speaking, is the temperature of the photons. Okay? And you already know what the temperature of the photons are today, so you can trace back what was the temperature of the photons back then. Anyways, okay, so you compare, you have here gamma, you compare with H, then I can do this here. So it's radiation, let's say just consider the photons, or something that behaves like, has a velocity close to the speed of light. So V that appears here, you assume that's equal C, the speed of light. But the speed of light in natural units for any particle physicist of any respect, C is equal 1. So it's natural units you always use. And the Hubble rate, I've just shown you what it is. So you just compare this. Remember, I'm just saying the radiation dominated era. I'm trying to compute the decoupling, or determine when the decoupling of some particle, which was radiation at some point, when that happened. So any particle which was radiation at some point, I need to determine what's this decoupling. When the decoupling happened, I need to compare with the expansion rate. And when it's not relativistic for now, the same. Doesn't matter. You have to compare always the interaction rate with the Hubble rate, always. Okay? All right, so I'm not telling you what this particle is. So H and then gamma and H, you compare, you get this formula here. And that's where the particle physics enters. So I don't know what sigma is. Sigma is the cross-section associated to that particle species. So now I know that neutrinos in the standard model, these neutrinos, these three flavor neutrinos that I was mentioning yesterday, these three flavor neutrinos have a cross-section which is about Fermi constant squared, energy squared. And then, but this energy I'm involved, I'm talking about at that time, the energy was related to the temperature. I'm not caring about the constant factors here, just order of magnitude, okay? Almost no constants I'm using. That's why I not using these Gn and reduce everything in terms of the reduced Planck mass. So there is no constants here involved except the reduced Planck mass. So just compare. Okay, since the cross section is GFE squared, which I can approximate to GF squared temperature squared. And then I have this formula, which is this one. The number density I haven't shown you, but the number density of a relativistic gas, this is statistical mechanics. You can get any relativistic gas, the number density of particles in that relativistic gas, proportional to the temperature to the third power. Okay, that's general. All right. So n is proportional to t cubed. There are some constants involved, which I don't care. And then you can find the decoupling temperature of that particle, which I said is neutrinos, where the neutrino information entered in the cross section. If you want to use another particle, then I put the cross section of that other particle. And then you find the decoupling temperature of neutrinos is 1 MeV. So Andre has mentioned this before, that the coupling was about 1 MeV, and that's the proof. Okay, so the coupling temperature of the neutrinos in the standard model is 1 MeV. Why is this relevant? Because what are the mass of neutrinos? About EV, less than that, EeV. So neutrinos, when they decoupled, they were hot relics. What I mean by hot relics is that their temperature of decoupling is much larger than their mass. That's what a hot relic means. And dark matter, as Fabio has shown, is cold. So just by this statement, neutrinos in the standard model cannot be the cold dark matter of our universe. Just by this very, very hard calculation, okay? Just that, I just shown. But now I have to prove to you that also the abundance, just a second proof, that the abundance of the neutrinos in the standard model is very small. So it cannot be the omega of 0.3. So it's very small. All right. So neutrinos are hot relic. This is the exercise. So I'm going to lead to you to prove this formula. So I'm not going to show today. You can ask me during the Q&A session. That if you assume that the universe conserves entropy, entropy is conserved throughout the expansion of the universe, you can prove that the abundance of neutrinos in the standard model is equal to, for neutrinos, you can find that their abundance squared neutrinos is the sum of the neutrino mass is about 90 eV. So the sum of the neutrino mass is below 1 eV. Below. So we know that's from cosmology, from whatever else. Okay? So we know that. And then you plug in that formula, like 100, so you get the abundance is about 10 to minus 3 or so today. But omega is 0.3. So neutrinos in the standard model cannot be the dark matter. It's the second argument for that. So in terms of number, it cannot be. In terms of structural formation, they cannot because they're hot. So you have two solid proof that neutrinos cannot be the dark matter of our universe. And that's very important for particle physicists because, look, now we really need to go beyond the standard model to explain the dark matter of our universe. So that's like get goosebumps talking about this, okay? So that said, any questions so far? Super easy at some point so far? Okay. All right. So let's complicate it a little bit. So for the neutrinos, this is done. There's nothing more beyond that. Okay? Neutrinos cannot be the dark matter of our universe, and that's done. Period. The standard model, the active neutrinos. That's how we call it. All right. So now let's understand a little bit of this decoupling, what this decoupling really is. So this was for a hot relic. So I just specified there was neutrinos when I refer to the cross-section. So before it was general, and I said, it's neutrinos, so let's put the cross-section of neutrinos. If I wanted to do something else, if you come up with a particle physics model and you have a hot relic, some particle which is relativistic in the early universe, just put the cross-section associated to that particle, you're gonna find the decoupling temperature. So that's easy. That formally stands. All right. So now for a cold relic, non-relativistic. So cold means is the opposite. So for hot relic, that's what we had. For cold is the opposite. The decoupling of a cold relic happens when mass of the particle is larger than the temperature of the coupling. Okay? So dark matter particles, which are cold in terms of particle physics, so I think, okay, the decoupling temperature is small compared to the mass. Okay? That's important because I can sort of infer what the mass of the dark matter particle should be in a particle physics model. All right. So, however, from statistical mechanics, again, you go back there and then you find that the number density is just not proportional to Q to the third power, to the temperature to the third power, has a Boltzmann suppression, which is this one. I don't know why it's very small. There should be a minus there. Minus exponential of minus m over t. Anyways, so if I define that a variable x is m over t, I'm just defining. And then cold relic, as I just defined, cold relic means that the mass is larger than the decoupling temperature. So I know that x should be smaller than 1. Sorry, much larger than 1 for a cold relic. And then I do the same exercise. So you're going to show that in the exercise I wrote to you. Gamma compared with the expansion rate, and you solve the formula. You get this one. So this is simple, it's straightforward, this step. The only thing you should care about is cold relic. Instead of Farinaldo, I was talking about hot relic before. The key step was the cross-section for the neutrinos. Now what is the cross-section of this cold relic? I don't know, I'm gonna make up a number. Let's say it's a cross-section similar to the standard model as well. The same for the neutrinos. Let's see what happens. Okay, so I'm gonna say this cross-section is also related to GF squared. The energy is squared, but the energy is now non-relativistic, so it's related to the mass. Mass is squared of that cold relic, which is this formula right here. Take a mass like similar to the Higgs, 100 GeV. What you find, guys, is this thing. Let me explain this plot slowly. So this thing on the y-axis is related to the number density of particles. And here I have x, m over t. What I'm saying is, so this is the plot of the number density, and this is x. I'm saying is this: when the expansion rate equals the interaction rate, these lines, horizontal lines, cross. So this points here is like when the number density is 10 to minus 8, and this is that's the value right there. When it's 10 to minus 14, that's the value right there. When it's 10 to minus 20, so they differ in different orders of magnitude. That's this point right there. Physically speaking, what I'm trying to say is the following. Whatever particle physics model you have, as long as the particle belongs to a thermal history, okay, whatever particle physics model you have, as long as it belongs to a thermal history, if the cross-section is like this, which means weak scale, the decoupling of that cold relic of that particle with weak scale interactions happens when those lines cross. And those lines cross for x either equal 20 or equal 50. Whatever particle physics model you have, equal 20 to 50. So this x, let's say, is about 30 on average. So whatever particle physics model you have, the decoupling temperature of that particle is around 30 for x equals 30. So that means that M, or you can find that the decoupling temperature of a cold relic is about 30 over the mass. But the mass, I said, is around 100 GeV, right? So you can get 0.3 GeV. So if the mass is, and then if you could ask, Farinaldo, if the mass is 1 TeV, would be very much different? Well, this depends. That's not the whole story. I was cheating a little bit because you cannot solve so easily. But what happens in practice is that whatever particle physics model you have, whether the mass is 1 GeV, 1 TeV, 100 TeV, the decoupling temperature will be around this X. I always usually call X as decoupling temperature. It's just, I'm used to call this decoupling temperature instead of T. Is around 30. Why is this compelling? Because you're saying, I don't care if you have supersymmetry, extra dimensions, you can have whatever, beyond the standard model physics you're talking about. The decoupling temperature, if it's belong to a thermal history, actually is around 30. That's compelling. Why? Because your model, doesn't matter which model you have, if you put this condition from the very beginning, belong to thermal history, your model becomes predictive because I can relate the temperature of decoupling to the mass. Okay? So the cosmological implications of whatever model you have are the same as far as astrophysics is concerned. Because for astrophysics, it matters when the decoupling happens, whether it's cold or it's hot. Okay? So as long as you have a particle which is called relic or belong to a thermal history of the universe, the implications to astrophysics will be roughly the same because these X's are always around 30. Okay? And as I said, look, they're yes. The blue lines I just said, I'm just telling you, I could put this number right here, 10 to minus 8. I'm just saying, which value is this one? Is this 10 to minus 8? So I'm just saying, this is 10 to minus 8, putting the thicks, 10 to minus 14, and this is 10 to minus 20. Because I choose what sigma is and m chi is. Go back here. So from this, I find this. Look just at this expression. This is this, right? Square root of x exponential of minus x, which is this plot right there, right? What does this depend on? 1 over m chi, reduced Planck mass, which you already know is a constant, and sigma. So if I fix sigma and I fix m chi, I don't know exactly how this thing scales with x. Okay? Which are just these plots here. So, but let's, as I said, any particle physicist would transfer everything to natural units. So to talk about GeV, so the number we've come up with, so this number right there, you got this decoupling temperature, or X, around 20 or 50. So that's the first thing you have to remember. All right. So happens this, if I assume that the particle, look, not talking about any particle physics model. This particle, whatever that is, neutrino, I don't care the name, I don't care. It's a cold relic. I'm just assuming it belonged to a thermal history in the universe. So if you assume that, just that, this statement, okay, let's compute the abundance of that cold relic without using any other input. This thing, I don't know. Okay, I can all write on the side? Fine. From cosmology, for those who are not familiar with these cosmological parameters, the abundance of a given species is given by the rho of that species divided by the critical density, which we already know what it is. So if that particle is non-relativistic, it's m times n. M is the mass of that species and the number density of that species. So you just use that formula, which is what I'm using here. And then you have some tricks. I'm not gonna prove that to you, but it's there. So I put this formula so you can look it up later and see how the steps were. You find that the abundance of a given species, whatever that is, let me emphasize this, whatever that is, cold relic, the abundance of that cold relic is related to, is about 0.2. So let me erase this. Sorry, Martin. The abundance. Remember, I don't care about the actual numbers, the precise numbers. It's about 0.3. XF is the freeze-out temperature, or the X is around 20 or 30, doesn't matter. So just the order of magnitude times a cross-section of 10 to minus 8 GV minus 2 over sigma. Yes. So in order to get this cold relic, in order to be the dark matter of our universe, that cross-section should be around 10 to minus 8 GeV. I just transferred the units. Yes. I'm not even talking about the mass. No, not for that one. I can integrate out the mass on that one. For a precise number, yes, but to have an order of magnitude, no. The only thing that matters to me is X. So yes, the M dependence appears there, but I refer to X. So remove the M dependence, because I know that whatever mass you're talking about, I didn't prove to you, but whatever mass you're talking about, this actually will be around 2050 or so. Yeah? Yes. Yeah, that's why, obviously, that's why it's appearing there. But you see the next point, yes? The point is that I'm not proving why this is 30, right? I'm not proving. But there is one plot where I'm going to prove this to you, exactly where this study comes from. The only thing you need to remember right at the moment is that just take for granted that whatever particle physics model I have, this X can be around 10 to 50 or so. So you say, Farinaldo, but if I change the mass here, and then it'll change X. Fine, but the T also will change. So the X will roughly continue to be the same. I'm not proving to you, but that's what's going to happen. So this X will be roughly 10 to 50. Doesn't matter which mass you're talking about. So doesn't matter which particle physics model you have. If it belongs to a thermal history, this X will be around 10 to 50. Okay. All right. So obviously, since I started, as you pointed out, with a Fermi cross-section, the Fermi cross-section happens to be this one, obviously. Fine, but this cross-section, you know what this is? If I go back now to these astrophysical units, so I'm not being a well-respected particle physics right now, is around 3 to minus 26. Why is this relevant? This is sort of, if you want to have an experiment and test weak scale dark matter, a dark matter that possesses interactions like the standard model particles you have to test this cross-section of sigma v 10 to minus 26. So every time you talk about, Fabio will talk about indirect dark matter detection, you say, look, this bound's getting close to 3 10 to minus 26. That's what he's talking about. Why is it relevant? Because he's testing whether the dark matter particle belongs to a thermal history in the universe. That's what you're testing at the end of the day. This 3 10 to minus 6 is telling you whether it was belonging to a thermal history. Okay? This thing is popping up here, I think was a failure of my part. All right, but let's see if we can find this similar cross-section in nature. As I just said, if you take the weak scale cross-section, which is the Fermi cross-section, Javier was mentioning, Javier, right? So you get the 10 to minus 8 back. Sure, I started with this number. Obviously, I have to get this number at the end. But that's not all. Now, let's take this weak cross-section and find this very important question for me. It's, okay, Farinaldo, maybe you have convinced me, maybe, that dark matter could have belonged to a thermal history in the universe. So what? From that statement, can I know what is the smallest or the lowest limit for the dark matter particle, and how heavy the dark matter particle can be, and how light the dark matter can be? Can I know, just from this statement, belongs to thermal history, nothing else? Can I know that? Yes, you can. Okay. So that's interesting because you're saying to your experimentalist friend, say, look, guy, you have to look in this window right here of mass. So I know where you're supposed to look for. There's this window right here. So this is predictive in this sense. So you, this experimentalist friend of mine told me that for experimentalists, it's like you have a truck and several roads. And to take the truck to a given destination is very, very expensive. So as an experiment, it's very, very expensive to make that road, take that trip. So a theorist said, no, look everywhere, because you can have all things, I can change this. And the experimenter said, no, you have to give me, I have the money just for one of them. Which road should I take? And then for these particles, which are called relic, I'm telling you exactly which road you should take. So that's why it's compelling from the experimental point of view. Anyways, so this lower limit, so I'm using that same formula I had before for code relic. Use this formula, so you have some tricks. This, remember, this cross-section about 10 to minus 8. If you just plug that number backwards, and then you find that these MK should be larger than 0.1 eV. So I'm saying if the dark matter belongs to a thermal history, in other words, has a cross-section around the weak scale, the dark matter particle has to have a mass larger than 0.1 eV. Okay? That's what you get. That's just analytically speaking. Okay? Not using structure information, anything, any data. Obviously, there are bounds from structure formation which tell you that neutrinos, so I'll be talking about when I discuss stellar neutrinos, that the masses of these particles which belong to a thermal history should be larger than about keV. Okay? But just from theory, the formal particle physicist, that's what you're going to get, 0.1 electron volts. And I say, what about the upper limit? This one will be exercised tomorrow. So this is very, for those who have learned a little bit of particle physics, the optical theorem. Who has learned the optical theorem before? Has anyone heard? Yeah, just 3. Okay. So it's just the following. The dark matter particle can interact with the standard the dark matter particle can interact with the standard model particles in many ways. I don't know which way it is. But the probability of interacting with all possible ways should be 1 when I sum all the probabilities. And this 1 tells me sort of what the cross-section, total cross-section at the end, maximum cross-section that the dark matter particle can have. And is related to its mass. When you relate this cross-section to the area, pi r squared, you can get that number here, which is telling you is that, I'm not going to prove this to you, it's an exercise for tomorrow. Well, it's not so easy exercise, otherwise it wouldn't be published in PRL in the 90s. Shows that if you have a cold relic, if a particle that belongs to a thermal history in the universe, the maximum mass that the dark matter particle can have is 100 TeV. So I said that we have a lower limit and we have a upper limit. So I'm telling which road you should take. Okay? Why? Because I'm not just telling which mass range I'm looking for. I'm also telling which cross-section you're looking for, which is weak scale. Okay? So you might ask some people who have studied dark energy models and so on from cosmology. Everything I've just said is only valid in the lambda CDM model. I said, wow, okay, just in the lambda CDM model. If I go beyond the lambda CDM model, it's a nightmare. Okay? So lambda CDM is very important. Yes. Yeah, it's an assumption. Thermally produced an assumption. So it's related to all that. But the point is, I can still have a dark matter particle which is thermally produced. If I change the cosmology, I will get different results. So you have a particle physics model. Your particle physics have never learned cosmology in your life. Your numbers you find there in your paper sheet can be very different if a cosmologist say, hey guy, the cosmology you assume in the background is different. So the numbers you find can be very different. So this is one of these modified cosmology things we're going to see maybe at the end of this lecture today. Anyway, so what I'm trying to say is this is like a spoiler for what's coming next, is that remember, I said that the cross-section, which was this slide here, here. The abundance of a cold relic dark matter particle is this, 0.3, and this cross-section, weak scale. This cross-section, I can increase and decrease this cross-section by a factor of 100 if I go beyond lambda CDM. If I exchange the expansion history of the universe somehow, I can increase and decrease that number. I can, instead of having 0.3 here, I can have a gamma, where gamma can be smaller than 1 or much larger than 1. Okay? And we're gonna go through each one of these steps, okay? Using either particle physics or cosmology. Any questions so far? So this is just to show you, this is a very complicated formula. So I'm not gonna prove this to you. Again, this is just so you can see how things are done. So Fabio has mentioned this Boltzmann equation. This Boltzmann equation is just telling you how much particles I have at the end. How much particles are produced throughout the expansion of the universe, considering the interactions, these particles' features, and so on. The number density of particles, that's all I get. So you can prove, that's a very nice exercise, that this term here, which is related to the how the universe expands, and this one is related to how these particles interact with other particles. Collision term. Well, I'm not going to prove this to you, but you can relate this thing, this very ugly formula, to the Hubble rate, n is the number density, and this collision term you can relate to the cross-section of that particle. So you have expansion rate on one side and cross-section the other side. So it's not much different from what we used gamma equal h before. Just more sophisticated. So this is the, you can, after some formula, I'm not going to show it to you. If you define Y as the yield, number density over entropy, you can find this formula, which is the famous Boltzmann equation using for particle physicists. I never use that formula, this and this one. I always use this one, because it's just simple to me. Why this is relevant? Now you're gonna see, you can forget all this formula, but you need to understand the plot that I'm gonna show you now. So from that formula, so I didn't make that formula up. From that formula you get the following. Let me see if I show here. Yes. Y, or yield, is number density over entropy. Okay, remember that. As a function of x that you know is m over t. The number density of particles in the early universe. So in the early universe, the universe was very hot, right? And the particles could be produced and would annihilate in equal rates. What I'm saying is, Orlando would interact with André and produce Fabio. Produce Fabio and Martin. So these guys could interact with each other and produce each other in equal amounts, okay? But at some point, some of these guys start to fight, or what I'm trying to say is the universe starts getting cold, or some of these guys are heavier than the other, right? A little bit chubby than the other. And at some point, one direction of this interaction is favored. So if these guys are heavy, they produce these guys. If these guys want to produce these guys, the universe has to provide enough energy for them to go back. But as the universe expands and gets colder, these guys are light, so cannot produce these guys. Therefore, this thing decouples, this interaction decouples. What I'm trying to say is the number density of these guys, Orlando and André, was sort of constant at some point throughout the expansion of the universe. So they were producing equal amounts to these guys. So But eventually, as the universe expands, the number density of them starts getting Boltzmann suppressed, which is for a non-relativistic gas, is exponential of minus m over t. Boltzmann suppressed, so I get rate and h. But eventually, as the universe expands, the Hubble rate equals the interaction rate, and these guys, Orlando and André, cannot meet each other anymore, and they decouple. So whatever is left of André and Orlando are here today, so they are the dark matter particles. So the number density of them became constant. So instead of being equilibrium, being Boltzmann suppressed, they decoupled, and that's what you've seen today, Orlando and André, which is the abundance of dark matter particle today. Okay? So if you think of Hubble rate and expansion rate when I was an undergrad, though I have to admit it was hard for me to understand. The way I understood it was, it's not perfect, but it was enough for me to understand. Was the following. Think of Hubble rate and expansion rate in terms of time, because Hubble rate is 1 over time and expansion rate is 1 over time in units. So you think of this. Imagine two particles are trying to interact and produce something else. But when they're trying to interact with each other, the universe expands before that happens. If they interact before that happens, they're trying to meet, but they can't because the universe expands before that interaction takes place. So they're trying to interact and they can't because the Hubble rate is too large. The universe is expanding, so moving them further away before they meet each other. So it's when that happens that these particles cannot interact anymore because the universe is always expanding when they try to meet. So that's what we call decoupling. All right, so this is the abundance, the omega that we refer as omega of dark matter being 0.3. But as I mentioned, this leftover abundance of dark matter particles, I know what H is, right? Depends on rho. But this is particle physics. This guy here, the interaction rate. So if I have a dark matter model where the cross-section of these two particles of Orlando and André are very strong, these guys fight all the time. So if they interact very strongly, gamma is very large. These guys will continue to be in contact with each other for a longer period of time. So what I'm trying to say is, if they interact very strongly, so you have here, so, and what is it? Sigma V, sigma V. What I'm saying is, if the cross-section with them is very large, they will remain in contact, will be equal to the expansion rate for a longer period of time. That means that this decoupling, this is very large, will not happen here, will happen here. If they interact weakly, as soon as the universe starts expanding, they will decouple. So the abundance of the sigma V is here. So what I'm trying to say is that depending on the abundance of dark matter particles you have left over, the leftover abundance of dark matter particles, you can relate to the interaction rate of these dark matter particles back then. So the sigma V, the annihilation cross section, or the gamma, is related to how much dark matter particles you have around today. So it's nice because I know that omega from cosmology is 0.3. So I know exactly what that sigma should be. And that sigma should be the weak scale. If, and only if, the dark matter particle belongs to a thermal history in the universe. Okay? In the lambda CDM model, nothing beyond that. There are some caveats to that. Okay? These caveats we'll be talking about later today. So is this picture clear? Where is the... No, doesn't matter. Doesn't matter what's the nature of dark matter, if it's a fermion or boson. Yeah, the idea is the same. So far, I'm just talking about the abundance of dark matter. I'm not talking about the nature of dark matter. So I don't care if it's a fermion, boson, scalar, complex scalar, vector, nothing. Real complex, doesn't matter. The details of the sigma V will change. So the sigma V will change because it relies on your particle physics model. So we've seen this weak scale, which is called sort of WIMP miracle, because you want omega to be 0.3. If you assume that the particles belong to a thermal history in the universe, you get the weak scale, or you can go backwards. If you assume it's weak scale, then they were in thermal equilibrium. So let's talk about these processes right there. So now it'll be, how much time I have? Okay, good. So now it'll be everything on the board. Let's talk about the production mechanisms for dark matter. So everything I've said, for instance, regarding the production of dark matter, I said it just happens if it is a cold relic and has a cross section around a weak scale, you get omega of 0.3. Yes, Javier? Is what? Doesn't matter. Yeah, he's asking if the particle, if matter is the dark matter particle is own antiparticle. No, because you can have a real scalar, which is particles antiparticle. You have the same thing. Real vector will happen the same thing. Okay. You have things which are called asymmetric dark matter, which they try to tie to the if the particle is own antiparticle, and then everything I said changes completely. But this statement of particle antiparticle is more general than asymmetric dark matter. All right, so this plot I've made, so let me just go back here. This is related to the sigma v. Omega is proportional to 1 over sigma v, because the larger the interaction rate, look, the larger the interaction rate, more particles will be in thermal equilibrium with standard model particles. And this curve, instead of being like this, is like this. This is the thermal equilibrium curve, which is Boltzmann suppressed. If there are particles which the interaction is very strong, they remain in equilibrium. So they'll trace this curve. And then if they decouple here, the number density will be small. If they decouple here, the abundance will be larger. And if they decouple here, even larger. Here, even larger. All right, so the abundance is inversely proportional to how strongly those dark matter particles interact, which is this one. But this thing in particle physics, if people make this general, this is wrong. This is not general, okay? This relies on one assumption that this production mechanism is 2 by 2. Means I have 2 dark matter particles in the initial state and 2 standard model particles in the final state. If I change this assumption, this relation can change. Okay? Just using particle physics. I don't care about the cosmology in this part. If I change the particle physics, if I make this 3 by 2 or 4 by 2, there are particle physics models that can do that. It changes. This relation here changes. Okay? So this WIMP miracle, it's not really a miracle because there are several layers, these assumptions to that. So it's the strong statement. So it's just saying that if it's, for me, it's already a very strong statement. If you assume that the standard model particle belongs to a thermal history, U is related to the weak scale. For me, that's already compelling. I don't need to say it's a miracle. Oh, look, the weak scale. No. You start with the weak scale. You assume it's in thermal equilibrium. So it's because you assume the weak scale without saying it's a weak scale. So there's no miracle finding the weak scale at the end. Like Javier pointed out, but when you start with the G firm in the beginning, yeah, sure. So it's not magic that appears the weak scale at the end. So it's not really a miracle. But it's still compelling anyways because it's predictive in the sense that you know the mass you should have, sort of the cross-section you should have, and the road for the experimentalist is determined. So this is the 2 by 2 process. So that's how it happens. So that's called the annihilation 2 to 2 processes. There. And there are things that still change, not this relation, but this number here that I said, 0.3. This is a weak scale. You can put here 0.3 if sigma weak scale. And this thing also changes. That's why it's not a miracle, I emphasize. If I assume this is not weak scale, can I have an abundance of 0.3 without assuming weak scale? Yes, I can, sure. Hundreds of models. All right, so what I'm gonna go back now to one topic they call 3 exceptions to the relic density. It's a very famous papers in particle physics in dark matter. They say, look, that was pointed out, I think was in what, 95, 96? This paper from Gondolo in Giamini was 96 or so some time ago. They realized there was a loophole in this thing. It's not really a miracle. You can change this scenario of 2 by 2. One of the things is like this. Now you go to relative particle physics, not about cosmology, astrophysics, anything like that. So this supposed miracle happens like this. If you have 2 dark matter particles that interact with the standard model particles, I related this cross section with G Fermi. So you have one dark matter particle here and one dark matter particle there. One standard model particle here, one standard model particle here, and 2 dark matter particles. So 2 dark matter incoming dark matter particles is 2 standard model particles at the end. And I said that this cross section was G Fermi squared m chi squared. But then I'm using the things that Andre was mentioning, how to describe the beta decay in terms of 4 fermions, a point interaction with 4 fermions. But it's not actually what happens in nature. You have mediators, these gluons, these gauge bosons at the end, they mediate the interactions between the dark matter particle and the standard model particles. So this thing can be this in reality. Whatever that is, some mediator. Okay, so I have a particle. So now let's resemble this to one plot that Andrea has made. Like this. Now I'm just gonna flip this diagram. Now replace this by dark matter and replace standard model. It's the electron and the Z can be whatever here. Just flipping the diagram. Okay? It happens that in particle physics, if this particle has a mass, it has a pole. It has a pole, it means is if the center of mass energy of the incoming particles matches the mass of this mediator, this cross section explodes. It increases dramatically. Okay, so it becomes very, very large. So happens that I said this weak scale, right? But this, I said x is around 20 to 50. The x is equal m equal m2 over t, right? X equal m over t. Is there? No. X equal m over t. And I said it doesn't really matter what m you're talking about, x will be always around 20 or 50. Okay. This is for the decoupling, but m is very important because dark matter particles are non-relativistic, so the center of mass energy of that process is related to the mass of the dark matter particle. The momentum of these dark matter particles are sort of irrelevant in this case, so the energy and mass are related. Therefore, if I pick a mass where this pole, this cross-section explodes, maybe I had a cross-section at the weak scale, but if the mass happened to be exactly close to the resonance effect, this cross-section, this abundance drops because omega is 1 over sigma. So if this cross-section eventually increases, because I picked a mass where this pole happens, this abundance decreases. So this is an exception, first exception to the relic density calculation, which refers to well, the details of a particle physics model do change the final answer you get at the end of the day for the dark matter abundance. Okay? So what I said, it's weak scale, so you get the relic density just right. Don't worry about. It's not quite true. So if you go to a concrete model, it does change, and it can change by a lot. Okay? So this cross section at the resonance can change by like a factor of 1,000. So if maybe you had omega of 0.3, but if you increase your sigma by 1,000, whatever model you have does not explain the dark matter of our universe. So you have to pick the mass in that model so that you get the omega right. Okay? So just to make sure that everybody understands, the particle physicists probably have seen this, but who hasn't ever seen anything related to pole with a mediator? Please raise your hand. Just you? Okay. Okay, so it's just there's the cross section of something like this. Goes as S minus M Z squared. S is related to the center of mass. If the center of mass happens to be equal to the Z mass, this thing goes to 0, so sigma explodes. So that's what I'm saying. And what is S? S is related to the dark matter mass, the center of mass energy. So if I pick the mass of dark matter particles such that this thing goes to 0, this thing explodes. And for the particle physicists in the room, this will be controlled by the width plus of the Z. Just for the particle physicists in the room. So the width of your mediator will control the abundance of the dark matter particle today. So this really goes to the detail of the particle physics, but let's forget that. I'm just saying that this WIMP miracle, we should just say if you have a cold relic, you get about right. It's not you get the relic density right. No, it's not you get about right the order of magnitude, and you have to pick wisely the model you have and the mass of the dark matter particle in your model wisely in order to get the omega 0.3. It's not for any parameter you can think. What the thing for us particle physicists who build models, 10 models over a month, is that, look, if I can pick so many models, I can build up many models easily. If you have one model, I say, look, whatever model you have, I'm pretty sure that if it's a cold relic, you're gonna find in your model some mass which gives you the omega 0.3. So it's just saying, okay, that's easy. I just need something which is stable, cold relic. The cross section is around the weak scale. I'm not saying which model it is. I'm pretty sure these models, depending on the choices you make, is gonna explain the dark matter of the universe. That's quite interesting for us because look, I can build many models, but you're saying every single model I make, as long as I start with these assumptions, I make these assumptions concrete, I can explain the dark matter of our universe. So that gives rise to a plethora of particle physics models, because you can have many particle physics models, many of them, where you can accommodate dark matter in our universe, just assuming that the dark matter was a cold relic and has a cross section around the weak scale. So the miracle stands for this: having any model you can think of, not that has at least satisfies these conditions of cold relic, has to be cosmologically stable. So I'm assuming you all know that from Fabio's lectures. But this is a cold relic, cross section around the weak scale. I don't care which model you have. You're gonna get at some part of this model you explain the dark matter of the universe. So it's interesting because this problem became really compelling at some point when we had fights between many models. And the fight between many models, for instance, left, right, supersymmetry, and so on. 331 model, some people here in Sao Paulo also work on that. And say, but my model is better than yours. And they were fighting over which model is better. But the point is, all these models, as far as dark matter is concerned, they can explain dark matter. Okay, so it was a way of calm down the ego, all of them, because say, look, all your models, they can explain dark matter model. The difference is that your model, the mass has to be this, and in your model, the mass has to be that. Because it was WIMP miracle, is satisfied anyways as long as you have a cold relic with cross-section around the weak scale. So whatever model you have, you can explain dark matter. This is key to understand that, because once you keep this in your mind, I'm going to go through exceptions to this case. If the dark, you can now, it's fun to change your assumptions and see what happens in physics in general. So you say, okay, Farinaldo, what else? What about if it's not a cold relic? If it's the expansion rate omega that you showed is different? What else if the dark matter particle does not interact with standard model particles? If the dark matter does not interact with standard model particles, can I still produce dark matter? Yes, you can. So what happens is this. So these conditions will be analyzed a little bit tomorrow, and then later we are going to the more focus on in particle physics, discussing which models we have. Okay, so we're gonna talk about, I'll focus on 3 of them. Maybe we won't have time, but you have the slides of all of them. So you can later go back at some point in your future, if you study dark matter, go back to those slides and see how things are done. Okay, so I think I'm done for the time. Thanks. Yeah.
I was wondering, you say that with the density condition, we can get the dark matter mass, but if you have a mediator, you can lower that mass because you can arrive at a weak scale cross section in a resonance.
Right.
That's
In a resonance, yes.
And for instance, if
Well, it's not just lower. You can also have larger, because a resonance is like this. So you can be on this side of the resonance or on this side of the resonance.
it being the interference region in the
Yeah. Okay. Because it's like Gaussian, if it's peak, so you can be on this side, on this side.
A question around there? Questions?
You can ask me after coffee. That's no problem. During the coffee break, no problem. Okay.
You can, but you'd
Yeah.
rather asking the question.
Yeah, you rather ask the question.
No, I mean, I don't want to. I mean, we want you to interact with the lecturers, right? So do look for them during coffee breaks. But if there is a question that may be of interest to everyone, then we can like postpone the answer. But look for them. Don't let them have like, coffee breaks. So
Yeah.
it's just to make sure. Okay, so if you have more questions, and okay, you can write down them, and we'll have the discussion session in the afternoon. And let's go for the coffee break.